All right, so we had been talking about kind of what you might think of as a simple investment model that really you can think of, if you wanted to think of there being a key driving force of that model, it really is the idea that there's an upward sloping supply of investment, right? And that's why the dynamics come about, because you can't, even if you wanted to have the stock of capital go, say, constant, jump up and then be constant again, you can't build it all overnight, okay? It reflects the fact that it's cheaper to build the product more slowly than it is to build it all at once, okay? And, you get a lot of reasons you can think about for that. You need some kind of other goods, capital goods to go in to produce the capital, that it's costly to move resources around, that there's, heterogeneity in the underlying resources, so the comparative advantage idea would give you upward sloping supply. There's a lot of ways to generate upward sloping supply, but the basic idea is no matter where it comes from, if I have upward sloping supply, then I'm going to want to spread out my production. I'm going to smooth my production over time to avoid, to reduce the total cost of production. And that really generates the dynamics as opposed to just, kind of living hand to mouth on capital and just producing the capital whenever you need it for production. And you can think about that as kind of a convexity in the cost structure, right? That is, you have a rising marginal cost. So rising marginal cost, of course, corresponds to convexity in the overall cost, right? And you could restate that problem. We did it as an equilibrium problem. You could restate it as a maximization problem. And for a lot of purposes, it can be useful to take what would be a competitive equilibrium problem and translate it into a maximization problem. And the simplest way to think about doing that is if you had a demand function, d of x, right? So you have some demand curve. Here's x, here's the price of x, here's d of x. Then you can think about, so this is an inverse demand function, right? Because if it's a function of the quantity, this gives you the height of the demand curve at a given point for a given quantity x. Think of that as like a marginal value schedule. Then you can say define v of x equals the integral from 0 to x of d of z dz. Okay, it's sort of the integral. It's the area under the demand curve. Then dv dx, of course, by the fundamental theorem of calculus, would be equal to d of x. That is, the derivative of this function v would be equal to the demand function I'm interested in. Similarly, on the cost side, if you had a supply function with the height of the supply curve, here's some argument x, call this supply function s of x. So again, it's the height of the supply function. It's an inverse supply function, actually. It's telling us the height of the curve at any given point x. Then what we could say is we could define c of x equals the integral from 0 to x of s of z dz. And of course, for that same reason, dc of x dx would be s of x, right? So in other words, if I had a supply function, I could think about it as corresponding to some corresponding cost structure. And if I had a demand structure, I could think of it as corresponding to some total value schedule. And so then if I wanted to think about a competitive equilibrium, I could think of maximizing what you might think of as a total surplus, maximized from 0 to infinity, e to the minus RT, V of k, if that's the capital stock at day t. So that's the value created by the capital stock at day t, minus, call it K of t, minus C of I of t, where that's the amount that I invested date t, dt. So I could restate my equilibrium problem as corresponding to this maximization problem. Right? So that would be my maximization problem. I'm maximizing what some people call this maximizing total surplus. This is the present value of the surplus created, where this is the value of the capital stock I have minus the cost of investment every period. So this is the surplus generated in period t. Okay? People understand how that works? And because I defined the value from the demand curve and I defined the cost from the supply curve, the derivatives of these things are going to give me my usual first order conditions. The first order conditions to this problem, I should say, are going to correspond to the equilibrium conditions of the underlying competitive equilibrium, right? This is a trick that we often use to restate a competitive equilibrium problem as a solution to a surplus maximization problem. Okay, and the reason it's nice to be able to do that is there's lots of algorithms out there, a lot of theorems we know about maximization problems that will then carry over to help us find the solution to this competitive equilibrium problem. Everybody understands that? So we started maybe thinking of it as a competitive equilibrium problem and say, well, that competitive equilibrium problem is really isomorphic. It's really identical to the corresponding maximization problem, the surplus maximization problem that looks like this. Okay? Yeah, so well, no, not quite. This won't correspond to the true surplus, right? In other words, what you might be saying is this V function I'm using isn't really the social value. But as long as it's the integral of the demand curve, it will generate the competitive equilibrium. It won't be maximizing the true social surplus, right? The true social surplus won't be given by this formula because this V won't be the true surplus function. But this V will give me the competitive equilibrium because the derivative of this thing is, you get the idea? I've integrated, I've just said, whatever the demand curve is, maybe there's externalities, maybe there's anything. I'm just going to integrate the demand curve, call that V, so that the derivative of that, the first order conditions of this are going to correspond to that equilibrium problem. All right, so there's a lot of time. Now, it's not always going to be true that every competitive equilibrium can be expressed as a maximization problem. There are going to be problems that can't. This particular one, like say K had some externality, that every time we produce K, it produces pollution, or I produce pollution. This would still give me the equilibrium, right? Because this is the first, what's the first order condition for this problem going to be? Well, we have to figure out how we're going to maximize this, right? So how would you maximize this function? Maximize integral 0 to infinity. I'm going to restate it just slightly. E to the minus RT, V of K of t, minus, I'm going to translate, what is I equal to? Well, what is the amount of investment? Well, that's delta K of t plus K dot of t, right? Everybody agrees with that? That is gross investment, which is I, is delta K plus K dot, okay? Because K dot, remember, K dot equals minus delta K plus I, right? So therefore, I is equal to delta K plus K dot, okay? So now let's look at what's the first order condition to this problem. Does anybody know? How do you maximize a function of K dot and K? Well, you remember the way to think about it is you can't think of K and K dot as independent choice variables, right? Because if you choose K dot, you've kind of chosen K. Like whatever K I started with, if I choose a path of K dot, well, that determines K, right? Because once I fix the initial condition, once I choose a K dot at every date, I've chosen what K is going to do. And it's nice to think about K dot as your control variable. That's the way people talk about it in these dynamic control problems. K dot is the thing I'm going to choose. Think about an economy. I'm trying to maximize this function. Each date, I'm going to choose a K dot. And what's my first order condition going to be? Well, think about it. Let's assume I have some candidate optimal path. This is K of t, some candidate optimal path, and I want to know what's the first order condition for that problem. In order for that to be the optimal path, what must be true? Yeah, that any variation of k dot is not going to make me better off. And since I could make k dot go up or I could make k dot go down, the derivative with respect to k dot better be 0 at every date. Because if the derivative with respect to k dot is positive, then I should increase k dot. If the derivative with respect to k dot is negative, I should reduce k dot. Of course, taking account of the fact that changing k dot changes k, right? I can't change k dot without changing k. So think about it. What if I was to raise k dot at one point in time? Just invest a little more at one date, holding k dot at all the future dates fixed. What would happen to my path? How would I perturb my path? If I increase k dot at one date, and then what I would do is I would pay the cost of increasing k dot at that date, and then I would get a little bit higher path. I'm trying to draw this parallel, but my drawing ain't so great. I would get a little higher path forever, right? I would, because I'm holding k dot fixed at all the future dates. I do a little more k dot today. I'm going to pay the cost of increasing k dot today, and then I'm going to increase my k forever, right? Everybody understands what the experiment. The experiment is I'm going to invest one more unit of capital today, and then I'm just going to keep that extra unit forever. And it better not pay to do that. But it better not cost to do that either, because that's got to be the first order condition for k dot at date t. Okay? Well, because I'm holding. Now, we can do it both. You can do it either way, right? And that's going to be a nice way. We're going to go there next. So this experiment is an experiment where I'm going to hold future k dot fixed. What does that mean if I'm going to hold future k dot fixed? It means I'm going to have to not only invest more today, but in order to hold that extra unit of capital, I'm going to have to invest a little bit more every year from now on. In fact, and we'll see that when we do the first order condition, right? Look at what's the first order condition going to be for that. Well, at date t, I'm going to increase k dot, right? So I'm going to get a minus e to the minus rt c prime at t, right? C prime evaluated at t. Everybody agree with that? That's the cost of increasing k dot. That is, I'm going to pay c. It's a negative because it's a cost. That's what's going to do to mine. But then what am I going to get from then on? From date t forward, I'm going to get e to the minus r tau. And what am I going to get? Well, I'm going to have extra k. I'm going to have, if I did one more unit of k dot, I'm going to have one more unit of k. So I'm going to get a v prime, okay, at tau minus, I'm going to have another unit of k, delta c prime of tau d tau. All right? And that's the answer to your question, is in this case, so I'm going to get c prime of t, which is the marginal cost of investing at date t, has to be equal to integral from t to infinity, e to the minus r tau minus t, v prime of tau minus delta c prime of tau. Okay? D tau. This, of course, is my marginal cost. So the marginal cost of producing a unit of capital, marginal cost, equals a present discounted value at R. And what is this? Anybody know what we call that? What is V prime minus delta C? C prime, sorry. What is that? Anybody know what that's called? It's called the net return on capital. right? That is the net return on capital, because it's how much that unit of capital returned today minus how much I had to pay to maintain it, because this is the maintenance cost, right? This is the cost of paying the depreciation on that capital. So you could say the marginal cost of investment has to be equal to the present discounted value of the net return on capital. So that's one way to look at investment. That's different than what we did, right? We did it a different way, but this is an equally valid approach. Now, the way we did it, we actually considered a slightly different perturbation than this one here. We considered a perturbation where you invested more in K today, increased K dot, but then I held investment fixed in the future so that stock then depreciated at rate delta. That would give us almost the same formula, but because the stock is going to depreciate in the future, I got to discount at R plus delta. So I would get marginal cost equals C prime of t equals the integral from t to infinity e to the minus R plus delta tau minus t. Then I'm going to get v prime of tau d tau, because there's no more. Remember, in that experiment, I'm holding investment fixed, so this doesn't change in the future. So I don't have to pay the cost of maintaining that extra unit of capital, but the loss from doing that is that capital is going to depreciate away now. Everybody understands? It's just a different perturbation. The first perturbation I did was you invest a little more today, and then you maintain that higher capital stock forever. That corresponds to saying the marginal cost of investment has to be the present value discounted at the market rate of interest of the net return on capital, because you have to pay the cost of maintaining your higher capital stock. Another way to think about the investment problem is that the marginal cost of capital, the marginal cost of investment, has to be equal to the present value discounted at R plus delta of the gross return on capital. This is a bigger number, right? Because you're not paying the depreciation. It's a bigger return, but you're discounting at a higher rate. And they're equally valid ways to look at the world, right? Because we could consider any perturbation we want, right? We could have increased the capital, kept it around for 37.5 years, and then disinvested then. That would give you a different formula, right? Any formula you want is fine. These are just two very convenient formulas to think about. One is invest in capital, keep it forever. The other is invest in capital, keep it as long as it lasts. The one formula we did in class before, with present value formula we wrote down, was invest and let it depreciate, right? Either one is equally good. The reason I bring them both up is because people make a lot of mistakes by confusing which formula they're using. They think about the gross return on capital, they think about the net return on capital, and it's either one is a perfectly valid approach to the world, just like real and nominal are equally valid approaches to thinking about the world. But if you're using real, you got to stick with real. If you're using nominal, you got to stick with nominal. Same is true with gross and net returns. If you're going to talk about gross returns, then you got to remember I'm using gross returns here. All right? So if I got gross returns on capital, I got to be discounting them at R and delta. On the other hand, my net returns, I could discount only at R. Right? You start mixing them together, you start getting confused. Okay? So be careful with that. But these are two equally valid approaches. And if we write down this problem, you can see this is our equilibrium condition, right? Because this is marginal cost of investment equal to the present discounted value of the net return, or equivalently, this is really the formula we use, the height of the supply curve equal to the present value of future rents. Okay. People got the idea that they're just, you can think about alternative deviations from our candidate optimal path. And, you know, the basic rule is you want to think about whatever, you know, since you can use the earning perturbation you want, use the one that's most convenient, the one that is the easiest for you to think about or use that expresses things in kind of a sensible way. Okay? Any questions that people?
This one keeps the K dot O was the same, but that one keeps the K dot O was delta unit.
Yeah, exactly. Think of this as hold I fixed. This experiment here holds I fixed. This one holds I fixed. This one holds K dot fixed. But holding K dot fixed and holding I fixed aren't the same because K is changing, right? That's the difference. You can hold net investment constant or you can hold gross investment constant, right? This formula was hold net investment constant, which is K dot. This one holds future gross investment constant. And if you hold gross investment constant, investing more today will then lead to a depreciating capital stock over time. It'll cause that extra depreciation to go away. On the other hand, if you hold net investment constant, you're telling me when you added that extra capital, I'm in the future going to invest enough to maintain that extra capital, right? So that's the difference between the two experiments. Now, they're equivalent. They're equivalent because you could think about a series of these experiments that would replicate that one, where every year you do the extra unit, and then every year you do that little delta experiment every year, and that'll just take you back and forth between these two formulas, right? Just two alternative formulas, okay? So, we could think about it the way you want, corresponding the way we looked at the world was here, right? That's how we looked at the world. We said, well, the marginal cost of investment has to be equal to the discounted value of future rental prices, because that's what the derivative of V is, right? V prime is just a rental demand curve. Discounted value of future rentals at R plus delta. You got to use both interest and depreciation. Okay? Any questions that people have about that? People understand how that works? Okay? All right. So that's one way to express our problem. And I want to introduce a slightly different problem that we can set up in exactly this same framework. So I'm going to get rid of this assumption that we have this rising supply price of investment, right? I had this model where the supply price of investment was rising, which meant we had this upward sloping short run supply curve of capital and also an upward sloping long run supply curve of capital, right? Because investment, if you want to maintain a higher capital stock permanently, you have to do more investment. If you have a rising supply price of investment, you have a rising long run supply curve. And in fact, we constructed the steady state supply curve for that model. I want to modify the model a little bit to what people often call an adjustment cost model. And the adjustment cost model looks like the following. Adjustment cost. Now you can combine adjustment cost with upward sloping supply, but I'm going to do the simplest version of adjustment cost. I'm going to have perfectly elastic supply. So I'm going to have the cost of any amount of investment I is just going to be P times I, where P is just the price of buying a unit of capital. So you can buy as much capital as you want at a fixed price P. Everybody understands that there's no upward sloping supply here, right? This is a horizontal supply curve of capital investment at price P. That is, the guys with the hammers are willing to build as much capital as you want, as fast as you want, at price P. Okay, but I'm going to need other. Now, if you just had this in our previous framework, what would the world look like? Well, the price of capital would always have to be P as long as we were making any investment, and the capital stock would be very erratic, right? If we needed more capital, we could just build as much as we want as quickly as possible. But I'm going to replace my upward sloping supply with a function that says there's some cost of adjusting my capital stock. That is, it's costly to increase my capital stock and it's costly to reduce my capital stock. So I'm going to have some A of K dot is going to be the cost of increasing my capital stock or reducing my capital stock. The most common one, and the one I'll use, is A of K dot equals 1/2 A times K dot squared. This is called the quadratic adjustment cost model. Okay? That is, it costs me something to increase my capital, and it costs me something to reduce my capital. And it has a rising kind of supply cost element to it because the faster I want to go, the more it costs per unit, right? Everybody understands? If I want to do twice as much adjustment, it costs 4 times as much. What that means is I would rather adjust at 2 miles an hour for 2 hours than at 4 miles an hour for 1 hour. It's going to cost me less to adjust more slowly. Everybody got the idea? That's the idea of the adjustment cost model. Now, there's a ton of other adjustment cost models you can come up with. You could use A times absolute value of K dot. Now, that is going to have some different properties, right? Because what is this? What's going to be different here? Think about it. There's going to be a marginal, A is going to be the marginal cost of going up and marginal cost of going down. So there's going to be a whole region of inactivity, right? There's going to be a region where it doesn't pay to go up because I got to pay A to go up, but I don't want to go down either because I got to pay A to go down, right? So it's going to have this kink in it at 0, but it also doesn't have any rising marginal cost either. That is, if I want to go 4 miles an hour for an hour or 2 miles an hour for 2 hours, it costs the same, right? It costs the same because there's an absolute value here. So the absolute value of 2 plus the absolute value of 2 is equal to the absolute value of 4. It doesn't really matter how fast you go in this model. It just, you don't want to go up and down. But if you're going up, you might as well go as fast as you want. Now, you could combine these models. You could make it so that you have rising marginal cost and this kink. You can make it so you have a fixed cost of adjustment, which is, it costs me something to adjust at all, and I just have to pay a fixed cost. Now, in that world, what would you want to do? Well, a lot of times you don't want to adjust, but if you're going to adjust, you might as well adjust a lot because you already paid the fixed cost, right? So there's a lot of models you can build. The far and away, the one that we've seen people use the most is this kind of quadratic adjustment cost model. This kind of a model has a very different long-run behavior than the model I just put on the board, okay? But let me explain why. Because now think about what our model looks like. Our maximization problem, same problem we had. We're going to max integral from 0 to infinity, e to the minus rt, v of k of t, minus, what did I call it? P times k delta k of t plus k dot of t minus a 1 over 2 k dot of t squared dt. Everybody agrees with that formula? All right. So now let's think about, what does this say our first order condition is going to be? What's our first order condition going to be? And let's make our life simple. Let's hold net investment constant. We're going to do the perturbation that I have on the board over there. We're going to hold future k dots fixed. So what's my first order condition going to be? What's my first order condition? Anybody tell me? Well, I got to differentiate with respect to k dot at date t, right? So I'm going to get an e to the minus rt minus, and what multiplies k dot? P plus a k dot, right? That's the marginal cost of investment at date t, equals plus, I'm going to get the integral of the future, which is the integral from t to infinity, e to the minus r tau, v prime of tau minus delta p d tau. Right? Everybody agrees with that? That's going to be my first order condition. Because remember, I'm holding future k dots fixed, so I'm not changing future k dots at all. So that would be my first order condition. So what do I get? I get P plus A k dot of t, which is really my marginal cost of investment, right? That's my marginal cost of investment, equals integral t to infinity, e to the minus rt, v prime of tau minus delta p d tau, and this is tau minus t, right? Because I just brought the e to the minus rt over the other side. All right. So it says I have my marginal cost of investment equal to that discounted value of net returns on capital, just like I had before. So viewed in the short run, this model looks almost exactly like my other model, right? Because I got a rising supply price here. The rising supply price is not coming because the price of capital is going up as I invest in more capital, but my adjustment costs are going up, right? So again, why do I slow down investment in this model? Not because I'm going to have to pay more for capital if I want to buy it faster, but because it's going to cost me more to put it in place if I try to put it in place too fast. I want to slow down that adjustment process. So that the kind of features we had of the model before with that rising supply price is still going to be there, right? If the demand for capital suddenly went up at date t, we wouldn't install all that capital day one. We would spread it out like we did in our model to spread out and reduce our overall adjustment costs. It's cheaper to adjust slowly than it is to adjust very rapidly. Right? We had that rising supply of capital in that case. Okay? Rising supply of investment because it's costing us more to put that investment in place in terms of these adjustment costs. All right? But now, think about the steady state properties of this model. What is the steady state going to look like? How do we find the steady state? We just set k dot equal to 0. And the steady state is going to be, what's the integral of this thing in a steady state? Well, that's a constant. So what's the integral of e to the minus r t tau minus t from t to infinity? That's just 1 over r. So we're going to get p on the left-hand side equals 1 over r v prime, and that's just the steady state v prime, right? Minus delta p. So v prime equals rp plus delta p equals r plus delta p. Which is, of course, saying in the long run, there's a perfectly elastic supply of capital. And that's the big difference with the other model that I put on the board. Right? The big difference with the other model is this model now, even though it has short-run upward sloping supply of capital, has long-run perfectly elastic supply of capital. And why? What's the difference? There's a sleight of hand in this model that is interesting. What's the difference? Yeah. Yeah, but why? Yeah, the first one had a rising supply of gross investment, whereas this one has a rising supply of only net investment. Yeah, I mean, it really is. It's a different, but it's an interesting question. Why would there be a rising supply price of net investment but not gross investment? right? It's you can build models, more fundamental underlying models that'll generate this. But that's the real structural difference. The real difference is one says, if you want to invest more in capital, I don't care if you're going to do it forever or you're going to do it short run, you have rising supply. This model says, no, only in the short run is there rising supply price of investment. In the long run, if I really want to always invest that much more, I can do it at constant cost. All right? People understand how that works? So that's the difference between this adjustment cost model. And sometimes people talk about it, I think the terms people use is internal adjustment costs, external adjustment costs. But the real economics is really about that whole question. Is I have a rising supply of net investment or a rising supply price of gross investment? That's really the difference between the two models. The first model had a rising supply price of gross investment. So if I wanted to invest more temporarily or permanently, it was going to cost more. This one has a rising supply price only of net investment. The adjustment costs are a function of K dot, not K dot plus delta K. Okay? But the dynamics of these two models look very, very similar because they both have this rising supply of K dot. If you want to increase K dot, you have to, it's better to do it slowly, have lower total cost of doing it slowly. Right? So now let me go to a third model. And this is going to be a model in which I'm going to have a single good economy. And that single good economy is going to have a single consumption good, Y, that we can split between consumption and investment. Now we're really starting to look like macro, right? That is, we're going to have Y, and Y is going to be split between consumption and investment. And we can think about this as like a representative consumer model. Maybe we're back with Robinson Crusoe on the island, and this is his Y. And he has to decide how he's going to divide his Y between C and I. And Y is just F of K. Okay, that's my model. So we're just abstracting away from labor. Just think labor's fixed. And opposite of course, the Malthusian view of the world. We're just going to think of labor fixed, and the world is all about capital. Okay? Well, what's the cost of investment in this model? That is, we don't have any marginal cost curve for investment. This has a constant supply cost, right? How much does it cost to make a unit investment? 1 unit of consumption. Right? That is, they're perfect substitutes on the production side, right? If I thought about our production possibility frontier between I and C, it looks like that, right? That is, we can produce any combination of C and I that we want as long as it adds up to F of K, right? Everybody agrees? That's the production possibility frontier. The production possibility frontier between C and I is linear, so a constant trade-off between C and I. Now, the model that we wrote down back when, you can think of as having some curve to this, right? That is, it costs more. As we wanted to invest more in I, it costs more C, right? That was our rising supply price model. This model gets rid of rising supply. It also gets rid of adjustment costs. So this model has no barriers to increasing capital as fast as you want. You could go all the way to here. Now, of course, if you wanted I equals F of K, what would that mean? That means C equals 0, okay? Not such a great idea, probably, right? Robinson Crusoe wants to eat, okay? So in this model, the rising supply price of capital is not going to come from the technology side of the problem. It's going to come from the consumption side of the problem. That if we want to invest a lot in capital, we got to sacrifice a lot of consumption. And the desire to smooth consumption over time is going to take the place of a rising supply price. Do you get the idea? We want to smooth our consumption out over time. So we are going to effectively have a rising supply price. That is, we are going to eat into our consumption, which is going to make consumption more valuable, which is going to limit the rate at which we're going to want to invest. Okay? So the limitation in this model on the speed of investment is that we're going to be sacrificing valuable consumption, and we want to smooth our consumption over time. Okay? So the cost of investing too quickly is that we'd have to consume too little for a while. Okay? And that desire to smooth consumption is going to cause us to spread out. So let me think about, well, how can we set up this problem? Well, pretty straightforward. I want to think about a consumer who wants to maximize the integral from 0 to infinity over his infinite future, e to the minus rho t. Okay, rho is the rate of time preference. You guys have all seen this, I'm sure. That e to the minus rt, u of c of t dt. Okay? That is, I want to maximize the discounted value of my utility over forever. Okay? People understand this model? Okay? And in this model, I'm going to have my technology. What is C going to be? C of t equals f of k minus I, right, of t. Everything's of t. Everybody agrees with that? C is just the difference between output and investment. So C of t equals f of k minus delta k minus k dot. That's going to be my consumption at date t is just output minus depreciation minus k dot. Everybody agrees? So max integral from 0 to infinity e to the minus rho t u of f of k of t minus delta k of t minus k dot of t dt. That's going to be my maximization problem. I want to maximize my lifetime utility. My choice variable is, what do you want to think of my choice variable? Probably k dot is a nice way to think about it. How fast should I grow my capital stock at any date t? Okay. What's my first order condition going to be? How do you want to do it? You want to hold future net investment constant? You want to hold future gross investment constant? Let's just hold future net constant. Hold a future k dots constant. Okay? So what's the perturbation? It's the one I have on the board there, right? We're going to increase k dot today, and then we're going to keep that extra k forever. What's my first order condition going to be? Minus e to the minus rho t. What's the cost of increasing investment today? U prime of t. Everybody agrees with that? That is, I give up a unit of consumption, which is worth u prime. That's how much utility I would have gotten today from that unit of consumption. That's the cost of creating another unit of capital. Right? The cost of investment is pretty clear. Foregone consumption. That's what I gave up. And then what do I gain? Well, from period t on, again, discounted, what am I going to gain? Well, what am I going to gain? I'm going to gain u prime of tau. And how much extra consumption am I going to get? Remember, I'm holding k dot fixed in the future. So what am I going to get? I'm going to get f prime k of tau minus delta d tau. Right? I guess I need another parentheses. Or I could have erased the first one or keep that one. But that's it. So my first order condition is going to be 1 equals the integral from t to infinity e to the minus rho tau minus t u prime of tau divided by u prime of t f prime of k of tau minus delta d tau. That's my first order condition. Anybody know what this is? What is that? What is that? It's just a market rate of discount between dates t and tau, right? This is going to be the market discount factor on consumption between dates t and tau. It's going to be equal to t to infinity e to the minus integral from t to tau of r of tau, r of s ds. Right, that's what it's going to be. Okay, so it's the integral of all those short-run discount factors between r of s, between t and tau, times f prime k of tau minus delta d tau. This is just a market, this is just a present discounted value of net returns on capital. These are the market discount factors from t to tau times how much you get at date tau. So this is the market value of those future net returns on capital. Remember, these are net returns. This is the market discount factor. Think about if r was constant. This would just be r, the e to the minus r, tau minus t. Right? So it's just a market discount factor over that period. You could write it as, if you wanted to think about there being a yield curve, you could think about this as r t to tau times t minus tau minus t, right? It could be that. It could be, this is the interest the interest rate between t and tau multiplied by tau minus t. That's what that integral would be. Okay? If you had a yield curve at date t. Okay? Or if you want to think about this as duration, call this r of s, where this is like some discount, where this is some duration factor, be the yield curve. What's 1? Why is there a 1? Yeah. That's the cost of investment. What's the cost of a unit of capital? 1 unit of consumption. It's the price of capital. Yeah, except for ours isn't even stochastic. Ours is less sophisticated than that. It's just like the discount factor, right? There's no stochastic element to it. It's today, it's the cost of a unit of investment, which is 1 unit of consumption, has to be equal to the present value at market prices of the extra consumption that unit of capital will produce, right? That capital over its lifetime has to produce back for you the same value as you put in, right? That's all it is. It's just that simple expression. It says the value of a unit of capital in terms of its future payoffs has to be equal to the cost of investment, which is 1 unit of consumption. Right? It's a very simple consumption-based valuation of the capital returns. You could call this an efficient markets hypothesis. You call it a zillion different things you want. They're all the same thing, right? It's how you value a basket of fruit, right? Right? There's nothing special about stochastic or time or any of those things, right? This is the way you value a basket of anything. You multiply them by their prices and you add them up. That's how you value, right? If I had a basket of groceries, what do they do when you go to the front of the grocery store? Right? They scan all the items and they add them up and they give you a bill. That's what this is. That's all this is. It's just basket of groceries. This is the groceries in the cart. These are the prices of the groceries, and they add them up. 3 cans of tuna and, 4 pounds of oranges and, a box of Tide. That's really all that's going on here. There's nothing else. There's nothing else. It's all that. That's all there is. All right? People understand? It's the same formula. All right? Anyway, so the guy at the grocery store knows how to do all this stuff. So he just doesn't realize it. That's all. Okay. All right. Why does this model have dynamics? Where's the dynamics coming from here? Think about it. Well, it's coming from you have to sacrifice capital. You have to sacrifice consumption, to get capital. And you don't want to starve yourself to build up your capital stock too quickly. And so what's going to happen is let's say I start with a low capital stock. Let's think about it. Well, we have to do our steady state. What's the steady state of this problem? Well, what's true in steady state? Go back to this equation. What's true in steady state? Well, u prime at tau is going to be equal to u prime at t because they're equal consumption. So that's going to fall out. This is just going to be a constant. So our steady state is going to be f prime of k minus delta over r equals 1. That's going to be our steady state. I'm sorry, over rho. Over rho equals 1, which implies f prime of k equals rho plus delta. Okay? It's going to tell me that the marginal product of capital has to be equal to the rate of time preference plus the depreciation rate. That's it. The marginal product capital equilibrium is only going to depend on these two numbers. What's your rate of time preference and what's the depreciation rate? How does that happen? What does that mean? So let's say, for example, go back to my previous way of looking at the world. Let's say we had a steady state. So my steady state, here's T, here's K, here's C, here's Y, and here's I. That's my steady state. Okay? That's my steady state. What would happen if suddenly we were to improve technology in this world? We were to, say, double F. We became twice as productive. What would happen to the steady state? What would happen to the steady state return on? Oh, I got to do that. I got to do F prime. Think about it. What would happen? Well, what would happen initially to F prime if we just doubled F? We just multiplied F by 2. Well, what would happen to F prime if I doubled F? Well, K isn't going to jump, right? K's got to stay right where it was. The minute after the function changed, we would have the same K, so F prime would double. And then what would happen over time? Well, where's our new steady state going to be? Well, it's going to be right back where it was. So we would then build up the capital stock and gradually bring F prime back, right? So our K would gradually increase until we reached our new equilibrium. Okay? Everybody agrees with that? That's what would happen. And of course, what would happen to Y? Well, what would happen to Y? Well, I would actually double initially 2x, right? That is, Y would double because we became twice as productive. We would produce twice as much output per person initially. And then what would happen over time? We would go even higher. As we added more capital, output per person would rise even more. Okay? But the return on capital would come back to where it was. So we'd have this very elastic and indeed perfectly elastic long-run supply of capital. That is, the supply of capital in this model is perfectly elastic, right? Because if the return on capital goes up, we just keep investing and investing until the return to capital comes back down to rho plus delta. We have a perfectly elastic supply of capital in the long run. In the very short run, of course, we have a perfectly inelastic supply of capital. Capital is fixed from where we got whatever K was yesterday is the same K we have to start today. Okay? And the reason we have this drawn out dynamics is because we don't want to consume too little in the interim. Right? All right? People understand that? It's going to limit the rate at which we increase. Now, one thing that's interesting in this model is we're not really going to be able to say which way C is going to go in this model because there's conflicting forces. On the one hand, you're richer. You're now twice as productive. You want to consume more. On the other hand, it pays to wait, pays to invest, so you want to reduce C. So C actually could go up or down. We don't know which way C is going to go, of course. I, of course, is going to have to go up because we have to build up the capital stock. So I is going to jump up, all right? And then which way I goes, but we're going to go to a new steady state on I, okay? Now for C, we don't know. We could either go down or up, but we know eventually C is going to have to go up, right? Eventually C is going to rise. But we may initially reduce C, we may initially increase C. Depends on how much curvature there is to our utility function, right? Depends on how willing we are to cut back on consumption. If our utility function is real curvy, we may actually increase C. We might say, geez, I'm richer. That's going to dominate this substitution effect toward consuming less. Okay? All right? This model is known as the neoclassical growth model. Now, it's not a growth model the way I wrote it down. It's a levels model. But the neoclassical growth model is a levels model that's been kind of jiggered to be a growth model, right? We just kind of added this technological change or whatever we wanted to turn it into a growth model. This is really the essence of the neoclassical growth model. The idea is we have a much more elastic long-run supply of capital, in this case perfectly elastically supplied. Now, what makes the supply of capital perfectly elastic here? Anybody know? Yeah, but that's part of the driver, but that's actually a hidden parameter. That is, we assumed that we had this additively separable utility function with a fixed rate of time preference. That is, the rate of time preference, remember, what do we call the rate of, what does economists generally refer to as, what do we mean by the rate of time preference? Yeah, but how do we measure it? In most models, we think about CT, call it CT plus 1. We think about the 45-degree line. We think about the slope of the guy's indifference curve as that point as telling us something about the rate of time preference, right? That's how it is in this model. Because the way you think about it is when you set consumptions equal, the trade-off between consumption at two dates depends by rho. So this model assumes that as we get richer, that rate of time preference stays the same, right? That is, as we get richer, the rate of time preference is the same. What if I modified this model and I made the rate of time preference fall as we got richer? That is rho. The rate of time preference would depend on how rich I was. Okay? The trade-off between consumption today and consumption tomorrow varied with how rich I was. And let's assume I made it fall as I got richer. What would be true about the long-run supply of capital now? Well, if you made it fall, but more importantly, the long-run supply of capital would now slope down rather than be constant, right? We wouldn't have perfectly elastic supply of capital. We'd have downward sloping long run supply of capital. Because as the capital stock grew, I'd be getting richer, and as I got richer, I'd be becoming more patient, which means I'd be willing to do more investment, right? So I actually would change this. My interest rate would, my marginal product capital would now end up below where it started. Even though I got more productive, I would accumulate more and more capital to the point where I got down to my new lower rate of time preference, right? It would be now the new lower rho plus delta, not the old level of rho. Okay? All right? So the logic behind the neoclassical growth model, and you can think about it as an adjustment cost model, right? It's an adjustment cost model. It's very much like my other adjustment cost model, where the adjustment cost came because if you want to move capital very quickly, you got to cut consumption, right? And I had this rising supply price because the more I invest, the more I got to cut consumption. All right. But when I look at a steady state, I don't have to worry about it, right? I mean, it may be that consumption becomes more valuable the less I have, or less valuable in terms of utility the more I have. But the trade-off between today and tomorrow, if consumption is equal, is not affected by that. It's affected by this rate of time preference, right? That is, I'm richer. Maybe that means in utility terms, I value consumption less than I did when I was poorer. But that's true for today and tomorrow. So it doesn't affect this trade-off that's going to drive investment. It's all about the rate of time preference. Okay? All right, so that's basically the idea here. So the logic of the neoclassical growth model is, in this kind of a world, because investment's fundamentally a trade-off between future and current consumption, that there's no real rationale per se that we should have rising supply price in that long run. It all depends. Whether we become more patient or less patient as we get richer. If we get more patient as we get richer, we'll have downward sloping supply. If we get less patient as we get richer, we'll have upward sloping supply. But it doesn't have much to do at all with the curvature of the utility function, right? Because in the steady state, there is no curvature. You're not really, you're not growing anymore. You're sort of at a constant rate. The curvature is going to tell me the dynamics of how I get there, okay? Just like that supply function was irrelevant in my adjustment cost model in the long run. The adjustment cost model, right? I had perfectly elastic supply. I basically assumed it was irrelevant.